Hello and welcome back. In this video, we analyze motion of an object with a constant acceleration. Consider an object A moving with the constant acceleration whose position vector at any instant is given by Ra equals xi plus yj plus ck, where x, y, and c are functions of time. Since the object is moving with the constant acceleration, it implies that the net force acting on the object, that is mass times its acceleration, is also a constant as per the Newton's second law of motion. In video 11, we have seen that the instantaneous acceleration vector is given by the rate of change of velocity vector. The scalar components ax, ay, and az of acceleration vector is given by the time derivative of scalar components of velocity vector vx, vy, and vz respectively. Equating scalar components of second law of Newton, we can write three scalar equations as fx equals max, fy equals may, and fz equals maz, ac. For an object moving with the constant acceleration, say 5i plus 1j plus 3k meters square per second, its scalar components ax, ay, and az are constant. That means this velocity component increases uniformly with time in the respective direction. That is, increases 5 meters per second in every second in x direction, 1 meter per second every second in y direction, and 3 meters per second in every second in c direction. Consider a car A moving with the constant acceleration in x direction in the xy plane. Since it is moving in x direction, we can say that the x component of position and velocity vectors are functions of time t. For this one-dimensional motion, we can derive a simple differential equation dx squared by dt squared as ax as kinematic equations that describe this motion. Solving this differential equation, we can find velocity and displacement in x direction as a function of time. The kinematic equation d square x by dt square equals ax can be integrated using initial condition dx by dt equals u at t equals 0, which is the initial velocity. We get equation 3, which is the velocity at any time t for this object moving with constant acceleration. Integrating equation 2 one more time and using initial and boundary conditions, we get displacement in x direction at any time t as xb minus xa equals v0xt plus half axt square, where v0x is the initial velocity in the x direction and ax is the acceleration, the x component of the acceleration vector. To better understand, consider this problem. A stationary cop measures instantaneous velocity of a car in a straight highway as 20 meters per second when it passes near to him. If the car is moving with a constant acceleration of 1 meter per second square, calculate the displacement of this car in 20 seconds and the velocity at this instant. Using the analysis previously done, we can calculate the displacement as 600i meters and velocity as 40i meters per second after 20 seconds of travel. Consider another problem. A ball is thrown vertically up from a tower with an initial velocity of 10i meters per second. If the ball misses the tower and hits the ground in 10 seconds, find the height of the tower. Since this is a one-dimensional motion in y direction with the constant acceleration due to gravity, the kinematic equation can be integrated twice to get an equation for displacement as equation 6. Substituting ay equals minus 9.8 meter per second square j. Given value of initial velocity v and time t, we get the displacement of ball in y direction as minus 390 j meters. Therefore, the height of the tower is 390 meters. Consider another problem. A ball is thrown vertically up from the tower of height 400 meters as indicated. Calculate the time of flight, velocity when it reaches the maximum height and at the bottom of the tower. We will solve this problem in class. In summary, for an object moving along a straight line in I direction with the constant acceleration ax, I, the displacement along the line for a time interval t is given by v0xt plus half axt squared, and the velocity at any instant is given by vxt equals v0x plus axt, where v0x is the initial velocity and ax is the acceleration. Thank you for listening, and keep watching the tied up video demonstrations of basic physics concepts.